All right, it's 12:15. Welcome back. So it's my honor to have Dr. Sara Rampazzi to give a keynote talk on sensor security. Sara is an assistant professor at the University of Florida. Her research areas include cyber-physical system security and privacy, embedded system design, modeling and simulation techniques with applications in healthcare, autonomous systems, and the Internet of Things. Her work focuses on investigating security risk and developing hardware and software defense strategy against hardware-based attacks. Her work has been covered by many media outlets such as New York Times and Forbes. She has received the Medtronic Outstanding Research Contributor recognition for medical device security and the Facebook Award Explorations of Trust in AR, VR, and Smart Devices in 2020. So let's welcome Sara. Sara, you can take it away.
Okay, so I'm Sara Rampazzi, assistant professor at the University of Florida, member of the Florida Institute of Cybersecurity, and my research and my lab focus on cyber physical system security and privacy. But today I will mainly talk about sensor security, what it is, what is changing, and what we expect is going to happen in the future. But before talking about security, let's face the elephant in the room first. We cannot talk about sensor security without mentioning the Internet of Everything. So Cisco coined this term in 2012 to describe a dynamically changing phenomenon that involves four main actors: people, things, data, and processes, combined into common, interrelated, and interconnected system. So the people interact with themselves and the surrounding via physical things, aka interconnected device, then intelligent system and other smart technologies process this data to understand what is called human issues and also deliver relevant content. But what it means, the aim of the Internet of Everything is to improve experiences and make smarter decisions. But what it means make smarter decisions for a machine, a computer, a connected device? Maybe a better term I will use is autonomous decisions. That's the ability of a system to be capable of performing autonomous computing and connecting to other devices, wired or wireless, for data exchange with partial or completely absent human supervision. For example, by using artificial intelligence algorithms to take decisions. But this system or system components needs to gather information about its status, the environment, the interaction with other systems and humans, in any given time to perform operations. So how it can be able to do that? Well, the answer is using sensors. So all the devices that we use every day have sensor in it, and in the future system we use sensor as well. Sensor has become the fundamental pieces that allow artificial intelligence-based systems to change the environment, change and adapt themselves, communicate with other systems, and with us as well. And the more these sensors become accurate, powerful, smart, the more the systems that use this sensor become capable of things never seen before, expanding their primary capabilities to become multi-purpose systems, such as machine learning-based algorithms, for example. For example, now we have cars that can automatically detect your health or predict your health condition when you are driving. We have smart home devices that can exchange data between them and outside the Wi-Fi range and between various homes. And very soon connected gadgets that can be controlled by our on top. And we are just at the beginning of this revolution. All this sounds exciting, But while the Internet of Everything is growing faster than ever, from a security perspective, it can become a living nightmare when critical autonomous decisions are made using erroneous or altered data from sensors. We continue to see this glimpse of this effect in the news. We had data centers that shut down because of loud sound a few years ago. That's because these sounds were inducing mechanical vibration that were affecting hard drives and the capability to write and read, and consequently causing the operating system to crash. We had several recalls of sensors of airbags and empty seat detection system because the normal car behavior were inducing erroneous measurement in the sensor, and thus tricking the software to trigger unexpectedly. And recently, we had the news of magnets of the new iPhone 12 able to deactivate implantable cardiac devices, causing issues in patients. But while many of these effects are unintentional, the things change a lot when we talk about deliberate attacks. So the more heavily we rely on sensors to gather data from the environment and from people, the more they become essential, and thus also are viable attack vectors. But when we think about sensor, a common assumption that we have is that sensors act as our own senses. Does camera capture light in a certain spectrum range as our eyes? Might be not the same range, but still is appear to follow the same behavior. Microphone can perceive audio as our ears, and so on. However, we cannot listen with our eyes, and definitely we cannot smell with our ears. And this is actually happening to you. I suggest to see a doctor immediately because something is wrong is happening. But let's consider now what it means attacking a sensor in this context. We are talking about attacks that doesn't involve tampering with the victim system, installing malware, or intercept communication, like the classical network-based attacks. We are considering here external signals able to alter the victim system behavior by exploiting sensors or electronic components flaws and vulnerabilities. This signal can be electromagnetic interference, light, sound, and other physical signals, or electromechanical vibration, crafted in a way to generate, overlap, or hide the legitimate stimulus that came from the environment, and provoke changes in the system that can go from the simple measurement errors to more complex manipulation of closed-loop connected system, with extreme case of systematically change the decision takes by machine learning-based models, like in object recognition, navigation, control, and so on. But why this happens? Well, the reasons are mainly two. In general, electronic components are affected by physical phenomena, and sensors in particular can perceive more than what we expect and what we designed them to do. I will show this example and two cases of this. So differently from traditional security threats that exploit vulnerability at the software or network layer, for example, these subtle alterations that exploit hardware nonlinearities or design flaw can remain unnoticed because the system is not able to recognize what is a legitimate signal from what is not. Furthermore, if the system is taking critical automatic decision, the attacks can propagate through the sensor to affect the machine learning-based algorithm that automatically become the final victim of the adversary. The sensor directly exposed to the external environment can become not only the primary victim of the attack, but also a medium used to compromise every system layer, from the electronic components to the high-level software application, to gain partial or full control of a system or the control over multiple connected systems. So classical security mechanisms such as software security, memory protection, authentication, or cryptography are not enough to eliminate these vulnerabilities. And also why, despite more than a decade of research on sensor security, it's still extremely difficult to build an effective and robust defenses against this type of attacks, especially because mitigation are often specific to solve a specific problem rather than consider a more broader scope. Generally speaking, there are many ways to attack sensors or the hardware components directly connected to it. And in general, nowadays, it means exploiting 5 main factors or a combination of them. So, for example, coupling, such as the capability to transfer electrical energy from a medium to another, usually at a certain frequency, called the resonant frequency. The typical example is using electromagnetic interference to couple with a cable and transfer AC voltage to the air into DC voltage in a cable. Another way is exploiting nonlinearities in the component design that, under certain conditions, can provoke a change in the component behavior, like in the case of the rectification that we see in the figure, for example. In other cases, the fact that when an electrical signal passes through a nonlinear component, it can generate subsignal that can transfer information as well. But an adversary can also exploit a certain periodic behavior to predict when the sensor will capture data and use it to inject malicious signals at the right timing. Finally, oversensing, such as the possibility that certain hardware act as an alter demodulator or converter to transform one type of energy to another. But in practice, these attacks have two major effects on output. Or they generate a new signal that can overlap or hide the legitimate one from the environment, or it sum or subtract as an offset to the legitimate stimulus to alter its shape. An example of how an attacker can use audio oversenses to gain control over connected system is exploited microphone or voice controllable system. These systems, such as Google Home, Amazon Alexa, or even to smartphones and tablets that use voice assistants like Siri, can perform many different operations like setting timers, ask for the weather, but also making online purchases and controlling other smart devices around the home, such as thermostats, smart locks, and even cars. This system works by recording an audio signal with a microphone, using speech recognition algorithms to parse the words out and then performing command based on that. So we have a small and cheap MEMS microphone that are used in all these devices, but also our phones and tablets. These microphones are usually exposed to the environment through acoustic ports like these tiny holes in the figure. These ports allow the acoustic pressure wave to pass directly to a microphone where they can be measured. In many of these microphones, a parallel plate capacitor is formed out of a movable diaphragm and a stationary backplate. So whenever the diaphragm moves in response to acoustic pressure, the capacitance changes. This change is then converted to a voltage signal by the onboard ASICs. So these voice controllable systems are designed under the underlying assumption that microphone can capture only acoustic signals, but in reality, it's quite different. So we discovered that MEMS microphones are sensitive also to light signal. In particular, the output voltage of the microphone is affected by lighting radiance due to a combination of acoustic and photoelectric effects in the microphone structure that naturally convert light into measurable voltage differences. Thus, by firing a focusing laser beam into the acoustic port at a different bright intensity, it's possible to change the microphone output voltage accordingly. So this is change the overall sensing of the microphone itself. So if we have an amplitude modulated light beam, it generates a voltage on the microphone output that follow the input signal in the audio frequency range of the microphone. So the higher the amplitude of the light signal in input, the higher is the amplitude of the output voltage signal with a very little distortion. This discovery has allowed arbitrary audio signal to be injected into microphone and make the attack possible. So then we recorded the audio of someone speaking a voice command, for example, "Okay, Google, what time is it?" And then played this recording, taking the voltage signal from the output of the laptop, amplify it with a simple audio amplifier, and then feed the signal into the modulation input of the laser current driver. The laser driver converts then the voltage into a current signal, and by driving the current across the diode, we generate this amplitude modulated light signal, representing the voice command. The device responded to the light as if someone has spoken the command. We tested different laser sources with different colors, from infrared to near ultraviolet, and the speaker replied to us every time. We then added optics to the laser to reduce the beam area at longer ranges and increase the irradiance that hit the devices. With the help of these optics, using a 5 milliwatt laser, namely equivalent to a laser pointer, we were able to achieve a successful attack to a Google Home device 110 meters away from the source. And also between buildings and through windows. So we test more than 17 different devices, from Google Home to various models of Amazon Echoes, to Facebook Portal, to Google Nest camera, and different models of smartphone and tablets. Beside each of them using different microphones, all were affected in the same way by the attack. But as we mentioned before, attacking sensor can be used also as a medium to attack other connected systems as well. We were able to execute unauthorized operation and affect other IoT devices connected to the voice assistant. We were able to unlock front doors, turn on and off lamps, change in setting of thermostats, and make purchases. We were able to open garage doors, unlock car doors, and even start the car engine. And more recently, at the end of the past year, enable and disable security cameras and test the more recent smart speaker. After almost 2 years from the vulnerability disclosure, IoT device can still be affected by this attack. And the reason is that while the software can be updated faster, sensor vulnerabilities involve a redesign of the hardware and overall software together that is difficult to achieve in a brief period of time. I did notice, though, the last generation of smart speaker released has changing something in the design, and the microphone ports are not exposed anymore. But with the hacker mindset, I also noticed that this month a new attack came out that used intermodulation, as we saw before, to send inaudible commands more than 2 meters away from the smart speakers, using electromagnetic interference instead of a laser. So even if the sensor is not exposed anymore, we can still be affected by adversarial signals. And the underlying sensor vulnerabilities are still there, ready for an adversary to exploit. But the problem of sensor security is even more deeper than that. We are able to attack not just the smart speaker, but also the device connected to it, also because a combination of several vulnerabilities, old and new, that together were causing multiple security issues. First of all, personalization and authentication are two very different concepts. For example, smart speakers are designed to be used by multiple users, so no authentication were present by default at the time of our attack, allowing any user to perform critical action, such as unlocking doors, using only voice, thus fully rely on the microphone sensor data. Only a personalization feature were present on these devices, but using this feature, were possible to train the system to distinguish our voice from other people's voices, personalize the device responses, and execute the selected action, like play a certain music when you arrive at home. Other voice assistants like Siri use speaker recognition by default. However, there are two main issues on this type of feature. First, we discovered that the recognition was easily bypassed using various online tools, like text-to-speech services, for mimicking the owner voice. Second, we discovered that the recognition was limited to only the wake-up word, like "Hey Siri," ignoring the rest of the command. Another factor that we noted in this exploit was the presence of routines and apps that can allow the device to do specific things they could not do otherwise, such as combining action that involves multiple devices. These features designed to augmenting the usability of the device and the overall facilitate the user interaction, but was in fact undermining the security of the system. Usually, some critical operations, such as unlock a smart lock, requires the user to speak a PIN number. But with these routines or services, were possible to bypass these security checks. For example, I was able to set up my system to unlock the front door and the alarm system when I use the sentence "I'm home" instead of asking for a PIN code or press a button. Finally, we encounter still common and old IoT security vulnerabilities. As I mentioned before, some unlocking or disarm operations are disabled by default for our security. And for execute them, you have to set up a n-digit PIN, which must be spoken before the voice assistant will execute action. We discovered that some smart devices doesn't require a PIN for certain operation, even if they can open to security threats, like open the garage door or open the trunk of a car. And usually we expect that after a number of wrong PIN attempts, the system will disable the feature and raise an alarm or block the operation. However, we were able to brute force PIN numbers, since there were no mechanism to stop the attempts after a number of failed tries. Or it was possible to set a PIN numbers of only one digit, very easy to guess with a few attempts. Even in these specific vulnerabilities has been fixed, new devices are released every day, and the security best practice can easily be overlooked. As another example, when attacking cars, connected to this voice assistant, we discovered that some application, official and not official, didn't require a PIN for unlocking doors, or neither key proximity. In one of them, there is no mechanism to prevent brute forcing as well. So why the technology in the Internet of Everything evolved faster than ever? All the well-known vulnerabilities sum to the newest one, and consumer electronics and sensors still remain unprotected against malicious attacks because of the exposure to the environment and the fact that the majority of the systems still blindly rely on sensor data. Thus, they can be attacked through these weak channels. And even more important, this confirms how the patch fix strategy is not a viable solution anymore in this evolving world. But what about artificial intelligence? How about machine learning-based techniques? How the sensor can affect machine learning models? Well, as an example on how an attacker can use sensor to affect the decision made by artificial intelligence models is what is happening in the automotive industry, and in particular in advanced driver assistance system in the past years, used in autonomous vehicles for obstacle avoidance. This system, as in drones and robots, use information collected by sensor, for example, LiDAR, cameras, and radars, to enhance the driver capabilities, but also to take partial or full automatic control of critical driving processing, like braking or steering or changing the speed of a car. There are several, tons of examples on how obstacle detection model can be fooled by adversarial example, like stickers on the road or adversarial physical object that we saw 2 days ago in the main conference. But sensor manipulation can be used as well to generate these adversarial examples. So if you think about a LiDAR sensor, for example, using the timing of the laser refraction to determine the distance from a potential obstacle, building a 2D or a 3D map of the surrounding. While this technology was very expensive and limited in use only for cars till few years ago, nowadays we have cheap LiDAR sensor technologies integrating our phones and VR system for augmented reality. So by exploiting the periodicity pattern of this sensor, we were able to conduct a simple relay attack to fake echo signal back to the sensor, to trick it into receive a real reflection from an object in a controlled way by adjusting the pulse timing. And use that to escalate to the next level by creating adversarial example able to fool the entire perception system, as you can see here, the Baidu Apollo system using in vehicles and autonomous vehicles, to see not existent obstacle. Without requiring to spoof entire shape of a specific obstacle, like a car or a pedestrian, but optimizing the attack to increase the probability of success with few numbers of spoofed echo signal as possible. As you can see in this picture, the adversarial example was a simple horizontal line. We had demonstrated at the time the possibility to stop a car in simulation scenarios, conducting two specific attacks. One for making the car automatically stop and activate the brakes, while the other by preventing a car to move in an intersection. But very recently, in the past month, we also demonstrate how it's possible to conduct this attack on moving targets in a realistic scenarios by tracking the sensor location, by using simple object detection models, and shoot laser pulses synchronized with the target speed and sensors, as you can see in the figure. So why the technology and the Internet of Everything evolve faster than ever? Also, attackers evolve to exploit new technologies to conduct attacks. And the hardware components and sensor can be used as an attack surfaces to affect intelligent system and machine learning-based technology. Thus, it's paramount to not only build more robust machine learning models to defeat adversarial example, but also protecting these sensors that makes in this model and use the sensor to gather in data. But most important, we need to stop thinking about hardware and software as a separate entities with their own separate rules and paradigms. In which way we can better trust autonomous system if we don't if we don't start from addressing the security of the fundamental pieces and considering hardware and software together as a whole when we research security strategies. Conducting this type of attacks needs to be the first step to build interconnected system resilient and trustworthy to current and not yet to be discovered attacks. And this starts also from a dialogue between software and hardware expert and manufacturer. We have seen in 2020 the convergence between cybersecurity and national security and a constant threat to critical infrastructure. The future, it will be artificial intelligence-based cyber attacks that start from connected devices. The impact of this attack will depend not only on the speed of adoption of emerging technologies, but also on the ability to secure them timely. So the pandemic can show us the world can rapidly change. Thus, as a security researcher, we need to be able to predict these kind of changes before becoming a new security threat. So why don't start from sensors? So thanks. shorter the presentation. Here we go. Oh, I can see some questions.
Great. Thank you so much for a great presentation. Um, people can post questions in the chat? Um, actually, can you shed some light on what is the major challenge in the area of sensor security? You said we need to consider hardware and software together. What do you think is the major challenge?
The major challenge is to understand that hardware behave different from software, and it seems there is like something obvious, but is not. As we can see in like commands, all these vulnerabilities are related to the fact that the sensor can perceive more than what we expect. So the characteristics on that depends on the physics of the electronics component, but also the environment where the system is immersed to. For example, the sensors in cars that were able to basically, or maybe this recall that happened to sensor in cars, that were tricked by measurement from the on vibration of the car itself that was misinterpreted. So we need to start to study on sensor to understand how to build even better software. Because if I have this changing in the behavior and like this interaction, how I can build a better software to compensate with some when something happens, or in which way I can address when something is trying to inject some signals. We have different ways to do it, but or maybe many techniques that start from detection, for example, and they can evolve in something more, and like there can be reconstruction of the signals. But to do that, we need to understand the physics. So I think this is the first step.
Sense. We got many questions in the chat. So let me just take them one by one. So this is one question from Virgil. What would be a countermeasure to these attacks? Use multiple sensors and never trust a single sensor's input?
I think this is one way to go, and there is like two different approaches. One is like only hardware. It means that you can have like check and control of the structure, like the electronic board itself. And it can be software. It means like a control of the input, like have policies, check or maybe or using, for example, algorithm then analyze the normal behavior so that you can detect anomalies. But you have different levels of this defense that can be basically combined together to build a more resistant defense. Because the issue is when you try to mitigate one, it can happen that can become another attack vectors that can be exploited. So you need to compensate this hardware and software at the same time. But yes, so maybe as you don't trust like processors, it can happen that you just assume that you don't trust every single sensor.
Okay, thanks. Another question from Joe Hans. Most of your attacks so far seem to be based on what happens if we shoot it with lasers. What are some of the other potential sensor vulnerabilities that you can think of?
So, as I mentioned at the beginning of the presentation, I'm not just only use lasers, but I use also like sound electromagnetic interference. So there are many examples in the literature and something that I'm currently work on that are based on different type of signal injection. And so, for example, one work on medical device that I recently published was um, how these temperature sensor that are using for patient control, in this case for infant incubators, and I think also Sharon, that from the university, professor of the University of Louisiana is here, and that can be used to manipulate and change closed loop system in this infant incubator. But I use electromagnetic interference from a certain distance, so remotely. And this can be an example. But yes, laser is more cool in a way, but definitely like every type of stimulus, external stimulus can be used as an attack vector.
Hmm. Okay, another question from James. How hard is it to convert some audio into an equivalent laser form?
So the conversion is done by modulating the current. So is automatically done in our cases by the driver system. So basically what you do is similar to an amplitude modulation, but like you're changing the current. And you change the current in based on the amplitude of the audio signals. Because
Okay,
lasers are driven by current and not by voltage. That's the difference.
yeah, maybe a relevant question is how expensive is those like modulator or measurement equipment?
So it depends. Or maybe definitely we had like in the beginning we use more like bench top instrumentation, like or maybe something designed specifically for that. But for example, like some module using light show can be used. So maybe at the end, the cheapest setup was around $300 for the driver, so something relatively cheap compared to like the actual setup. And for laser, or maybe a 5 milliwatt laser was a laser pointer, so a few dollars.
Okay, um, I guess many more questions. One question from Matthias. How will we update sensors?
So it's difficult. This is a very good question. And update electronic device is difficult. It depends on the technology, and it depends on like a balance between the cost and the actual system. So for IoT, the problem is there are mostly cheapest device, and the sensors that are using are cheap for this reason. So, for example, at the beginning, it happened that the researcher and the chip designer recognized that this kind of MEMS microphone were susceptible to light interference. So exist in a certain like a commercial products where you have this kind of sensor that are resistant on interference. But the difference is how expensive the device is, how expensive it is to actually integrate an hardware defense. So it needs to be a combination between the two. But when it's not possible, or maybe like the goal, and this is like the goal for our research in security, should be find an effective way to mitigate these attacks. And that can become from software and hardware together. So this is the way to go. And the technology needs to change to include security.
Okay. Then another question from Ryan. How do you think these attack modalities and the new sensor arrays and types will affect present and future augmented and virtual reality system.
Yes, so as I mentioned, talking about the LiDAR, these sensors are more and more cheap because the technology has changed. The technology of the LiDAR has become less expensive and is using for like augmented reality system, for example, for like face recognition technology, is using higher sensors or thermal cameras. You have all this new technology that is available right now at lower cost. And for example, when we think about the future of a virtual reality system, we are thinking about systems that are more integrated with our environment. So the pandemic has increased a lot this kind of product and development. So this can basically escalate on this kind of new feature.
Okay. One more question from Iranian. What is the actual physical effect that makes the MEMS microphone receive light? Was this
So there,
previous
Mhm.
yeah,
Sorry,
was this previous known as a reliability problem in MEMS microphone?
so there are two different things. The that this kind of MEMS microphone can also be susceptible to light is due to two main effects. One is the photoacoustic effect and one is the photoelectric effect. One is on the ASICs, one is on the membrane, and you have differences and different levels of one is the effect that is predominant compared to the other in based on the physical characteristics because the structure of the microphone changes. So it's a combination of multiple effects. That's why it's like difficult to fabricate a chip or a sensor that can actually avoid this problematic in the first place.
Okay. I guess are there any more questions? I think we already have so many questions.
I'm so happy.
Yes, thank you again for such a great talk.
Sorry again for the beginning, like it
Yeah, I
was a
think
little bit.
it finally works and went well.
Okay, thank you, and thanks to Woot.
Thank you so much, Sarah. Okay, I guess we can have some short break and then we can be back at 1:30. Yes, we can be back at 1:30 and we have uh, two two consecutive sessions without a break starting at 1:30 and then we will conclude the workshop.
Thanks. Yeah, I would also suggest that the speakers of the next two sessions try to start sharing so that we can add them to the list. And thanks again, Sarah, for an amazing talk and accepting it to give a keynote here.